Our universe might be a fleeting vibration in an endless, invisible sea. This is the startling premise of quantum fields, the fundamental fabric of everything. By the end of this journey, you will see reality in a completely new way. We will explore 30 theories that stretch from the origin of mass to the possibility that our cosmos is a single bubble in an infinite multiverse. Why does the vacuum of space hold a secret energy powerful enough to tear the universe apart? And what does it mean that empty space is not empty at all? What single idea about our world feels the most mysterious to you right now? Forget the idea of tiny, solid balls of matter. The true nature of reality is far stranger. Underlying the universe is a set of invisible, fluid-like entities that stretch across all of space and time. These are the quantum fields. Think of them as a vast, cosmic mattress, an energetic substrate that exists even in what we call a perfect vacuum. This mattress is not made of matter, but of pure potential. What we perceive as a particle, like an electron or a quark, is not a tiny speck sitting on this mattress. It is a localized vibration within it, a tiny spring that has been jiggled into existence. A calm, undisturbed region of the field represents empty space, while an excitation or a wave in the field is what we detect as a particle. This single shift in perspective changes everything. It means that an electron is not a thing that moves through space, but a specific, rippling quality of the electron field itself. The solidity of the world around you, the chair you sit on, the screen you are watching, all of it is an intricate dance of these vibrating fields. This idea forms the absolute bedrock of modern physics, replacing the ancient notion of indivisible atoms with a universe that is fundamentally energetic and fluid. How can something so seemingly solid be nothing more than a temporary pattern in an invisible sea? This invisible cosmic mattress holds a secret ingredient, a special field responsible for the very substance of our world. Think of empty space not as truly empty, but as filled with an invisible, treacle-like energy. This is the Higgs field. Its existence answers one of the most profound questions in physics: why do particles have mass at all? Without mass, every particle would simply fly through the universe at the speed of light. There would be no atoms, no stars, no planets, and certainly no us. The Higgs field gives the universe its texture and weight. The way it works is beautifully strange. Imagine a vast, endless party filled with guests. This is the Higgs field. Now, imagine a famous celebrity trying to walk through the room. The moment they enter, people crowd around them, grabbing their attention, slowing their progress. This interaction, this resistance, is what we experience as mass. A particle that interacts strongly with the Higgs field, like a heavy-top quark, is like that major celebrity, moving slowly and with great effort through the cosmic crowd. A particle that interacts only weakly, like a photon of light, is like an unknown guest who slips through the party completely unnoticed, moving at the ultimate speed limit. The celebrated Higgs boson, discovered at the Large Hadron Collider at CERN, is not the field itself, but a tiny, temporary vibration in it. Its detection was like finally seeing a single splash in the invisible ocean, confirming that the ocean was really there. This discovery was monumental, validating a decades-old theory about the origin of mass and completing a crucial chapter in our understanding of the fundamental forces. It means that the weight of everything you see, feel, and are stems from an unseen interaction happening everywhere all the time. What other invisible forces are shaping your reality right now without you ever knowing? This cosmic mattress of fields is not just a poetic idea. It is described by a precise mathematical language known as quantum field theory. This framework is the powerful fusion of quantum mechanics and Einstein's special relativity, and it gives us our most complete picture of the universe's fundamental workings. It is the engine behind the standard model of particle physics. In this view, every type of elementary particle is a quantum, a discrete bundle of energy of its own unique field. The electron is a quantum of the electron field, a quark is a quantum of the quark field, and so on. The entire universe is thus a symphony of these intertwining fields, with particles appearing as the individual notes being played. The predictive power of this theory is breathtaking. It did not just catalog the particles we knew, it demanded the existence of new ones. Theorists predicted the W and Z bosons, the carriers of the weak nuclear force, long before they were spotted in a detector. They foretold the top quark and the charm quark, and of course the Higgs boson itself. Each discovery was a stunning confirmation that this mathematical framework was describing reality itself. The Standard Model encompasses everything from the photons that bring us light to the gluons that glue atomic nuclei together, painting a picture of a reality that is both deeply strange and profoundly elegant. How is it that mathematics, a human invention, can so perfectly map the behavior of these invisible cosmic fields? This elegant mathematical framework, however, hides a terrifying secret. Our most trusted equations, which so perfectly describe the quantum fields, also predict that the vacuum of space should be bursting with an unimaginable density of energy. This vacuum energy should be the most powerful force in the cosmos. According to quantum field theory, empty space is a seething, bubbling foam. Virtual particles pop in and out of existence in a frantic, endless dance, borrowing energy from the vacuum for fleeting moments. All this frantic activity should imbue every cubic centimeter of nothingness with a colossal energy density. The calculation is straightforward and the result is staggering. It suggests the vacuum should possess an energy so powerful that it would have ripped the universe apart in a fraction of a second after the Big Bang. The universe as we know it should not exist, yet when we look out at the cosmos we see something entirely different. The energy of empty space is not a cataclysmic force of destruction. Instead, we observe a much weaker phenomenon, a gentle pressure that is pushing the galaxies apart, accelerating the expansion of the universe. We call this dark energy. The problem is the gap between prediction and observation. The energy density we calculate for the quantum vacuum is about 1 followed by 120 zeros times larger than the energy density we measure for dark energy. This is not a small error. This is a miscalculation of epic proportions, a discrepancy so vast it is often called the vacuum catastrophe. It is the single worst theoretical prediction in the entire history of science. How can our most successful theory be so spectacularly wrong about something so fundamental? This vacuum catastrophe is a clear sign that we are missing a monumental piece of the puzzle. Perhaps our understanding of the quantum vacuum is deeply flawed, or maybe dark energy is not the energy of the vacuum at all, but something else entirely. This gaping hole in our knowledge forces us to confront the possibility that reality is far stranger than our equations can currently capture. This staggering error in our calculations leads us directly to one of the most famous stories in all of science, a tale of a presumed mistake that has returned to haunt us. It centers on a number Albert Einstein introduced into his equations of general relativity, a number he later called his biggest blunder. He called it the cosmological constant. At the time, Einstein believed the universe was static and unchanging. His original equations, however, predicted a universe that should either be collapsing under its own gravity or expanding. To force the universe to stand still in his calculations, he added a fudge factor, a repulsive energy inherent to the fabric of space itself that would counterbalance gravity's pull. When the universe was later discovered to be expanding, Einstein discarded the idea as unnecessary. But decades later, with the discovery of dark energy and the accelerating expansion of the universe, the cosmological constant made a triumphant and deeply puzzling return. It turns out Einstein's blunder was prophetic. The cosmological constant is the perfect mathematical representation for the energy of the vacuum. the very thing that causes our catastrophic calculation error. The problem is not its existence but its size. Why is the value of this constant so incredibly small, yet not quite zero? To understand the sheer improbability of this, try to picture a cosmic balancing act. Imagine you had to balance a perfectly sharp pencil on its tip, not for a second but for billions of years. Now, place that pencil not on a table but on the scale of the entire observable universe. The fine-tuning required for the cosmological constant to allow for a universe like ours, a universe with galaxies, stars, and planets, is even more precise than that. If the vacuum energy were just slightly stronger, that repulsive force would have blown matter apart before it could ever coalesce into the first stars. If it were slightly weaker and negative, the universe would have collapsed back on itself in a catastrophic crunch long ago. Our universe exists in a breathtakingly narrow window of possibility. So how do we solve this puzzle of impossible precision? One proposed solution lies in a beautiful symmetry called supersymmetry. This theory suggests that for every known particle we have discovered, there exists a super-partner particle. This cosmic pairing would have the elegant effect of making the positive and negative contributions to the vacuum energy almost perfectly cancel each other out, bringing the theoretical calculation much closer to the tiny value we observe. The catch is that we have not found any of these super-partner particles, leaving this elegant idea in limbo. Another, more philosophical solution is the anthropic principle. This suggests that the cosmological constant has the value it does because we are here to observe it. In this view, our universe is just one of a vast multiverse, an infinite collection of universes, each with different physical constants and different values for the vacuum energy. In the overwhelming majority of these universes, the constant is too large or too small for life to ever arise. We, quite naturally, find ourselves in one of the rare, finely tuned universes that permits our existence. Is our cosmos a product of incredible, precise luck, or are we simply one outcome in an infinite cosmic lottery where every possible reality plays out? The vacuum catastrophe reveals a cosmos balanced on a razor's edge, but how did the universe achieve such a delicate state? The answer may lie in a transformative process that reshaped the cosmos in its earliest moments, a concept known as spontaneous symmetry breaking. This idea sounds abstract, but we witness its effects every day. Picture a perfectly round dinner plate balanced on its edge on a table. From above, the plate looks the same no matter which way you turn it. It possesses rotational symmetry. But the moment it tips over and settles flat on the table, it has chosen one specific orientation. The perfect symmetry of the balanced state is broken, not by an external force, but spontaneously through the system's own instability. The universe underwent a similar transformation. In its first fraction of a second, all the fundamental forces we know today, except for gravity, were unified into a single, supremely symmetric force. The cosmos was a formless, ultra-hot soup where particles like the photon and the W and Z bosons were indistinguishable. This state was symmetric but unstable. As the universe expanded and cooled, it went through a cosmic phase transition, much like water freezing into ice. Liquid water looks the same in every direction, but when it freezes, the water molecules lock into a rigid crystal structure, choosing specific orientations and breaking the liquid's rotational symmetry. In the early universe, this transition was governed by the Higgs field. To visualize this, think of a landscape shaped like a Mexican sombrero, with a high point in the center and a circular valley running around the brim. A marble sitting at the very top of the hat is in a symmetric but precarious position. The slightest nudge will send it rolling down into the valley where it comes to rest at one specific point. The marble has spontaneously chosen one location out of an infinite number of equally possible spots around the circle, breaking the perfect symmetry of the hat. This is precisely what happened to the Higgs field. As the cosmos cooled, this field settled into a stable but non-zero value everywhere in space, a state often called a false vacuum. This single event, the electroweak symmetry breaking, shattered the primordial unity of the forces. The electromagnetic force and the weak nuclear force suddenly appeared as distinct entities. Crucially, this process is what gave mass to the W and Z bosons through their interaction with the now active Higgs field, while the photon remained massless. This single, spontaneous breaking of symmetry is the reason we have a universe with diverse forces and massive particles that can form atoms. It was a cosmic decision that set the stage for everything that followed. What other hidden fractures in reality's fabric determine the laws we take for granted? This spontaneous breaking of symmetry set the stage, but it was another quantum field that truly sculpted the cosmos we see today. The inflationary field is a theoretical entity proposed to explain one of the universe's greatest mysteries, its large-scale uniformity. When we look at the cosmic microwave background, the faint afterglow of the Big Bang, we see a sky that is almost perfectly smooth. Distant regions of the universe, which should have never been in contact with each other, have the exact same temperature. How could this be? The answer is a period of breathtaking, exponential expansion in the very first fraction of a second. Driven by the potential energy of a primordial quantum field, the infant universe did not just expand, it inflated. In less time than it takes to blink, a region of space smaller than a subatomic particle was stretched to a size larger than our entire observable universe. This violent stretching smoothed out any initial wrinkles, ironing the cosmos into the uniform tapestry we observe. But like all quantum fields, the inflationary field was subject to tiny, random fluctuations. These quantum jitters, stretched to cosmic proportions by inflation, became the seeds for all future structure. The slightly denser regions in this early fog became the gravitational wells that would eventually pull in matter, forming the vast cosmic web of galaxies and galaxy clusters we see today. Every star, every planet, and every one of us originated from these microscopic quantum tremors. The mechanism of inflation, however, does not just stop neatly. The theory suggests that in most of space the process is eternal. Think of a pot of water beginning to boil. As it heats, bubbles of steam form and expand. In this cosmic analogy, our entire universe is just one such bubble. The boiling water is the inflating field, and each bubble is a region where that field has decayed, settling into a stable state and creating a universe with its own local laws of physics. This is the multiverse. In this breathtaking vision, our cosmos is not everything. It is just one bubble in an infinite, frothing ocean of space-time where new universes are constantly being born. In some of these bubbles, the strength of gravity might be stronger, or the mass of an electron might be different. Some might have 4 fundamental forces, others might have 6. The constants we hold as universal and immutable might be mere local bylaws, the unique outcome of how the field settled in our particular cosmic bubble. The multiverse is not a place you can travel to, as it exists in a realm beyond our space and time. It is a consequence of the relentless driving force of eternal inflation, a quantum process that may have no beginning and no end. If our universe is just one accidental paradise in an infinite foam of realities, what does that say about the nature of existence itself? This cosmic foam of bubbling universes suggests that our physical laws might be local accidents, but what about the invisible matter that holds our own galaxy together? Most of the mass in the cosmos is not made of atoms or any particle we have ever seen. It is dark matter, a ghostly substance that reveals itself only through its gravitational pull. One of the most compelling candidates for this cosmic phantom arises not from a new force, but from a solution to a deep mystery in an old one. This is the action, a hypothetical particle born from the need to fix a puzzling asymmetry in the strong nuclear force, the force that glues atomic nuclei together. The equations of the strong force allow for a certain kind of asymmetry, a process that would make the neutron, a neutral particle found in every atomic nucleus, possess a tiny electric dipole moment. This would mean the neutron is ever so slightly positive on one end and negative on the other. Yet, incredibly precise experiments have measured the neutron and found it to be perfectly symmetrical, its electric charge distributed with perfect balance. This is the strong CP problem. Why does the strong force appear to respect a symmetry that its own laws say it should break? The proposed solution is a new quantum field, the action field. This field would naturally adjust itself throughout the cosmos, cancelling out that unwanted asymmetry and leaving the neutron perfectly round, just as we observe it. The action particle would be the tiniest possible vibration in this cosmic correction field. Unlike the heavy particles of the standard model, the action would be incredibly light, potentially trillions of times lighter than an electron. This extreme lightness makes it a perfect candidate for the cold, slow-moving dark matter that seems to permeate our galaxy. Think of the action field not as a dense mattress, but as a vast, invisible sea of incredibly gentle waves. These waves would not interact with light or ordinary matter in any significant way, which is why they have evaded detection for so long. They would simply be there, filling every corner of space, their collective gravity providing the scaffolding upon which galaxies are built. To find them, physicists have built some of the most sensitive detectors in the world. Experiments like the Action Dark Matter E experiment, or ADMX, are essentially giant, high-tech radio receivers tuned to listen for the faintest signal. They use a powerful magnet to try and convert these ghostly actions into a tiny, detectable microwave photon. It is like trying to hear a single, specific whisper in a hurricane. The hunt is on throughout our galaxy, searching for the faint vibration of a field that might solve two of physics' greatest puzzles at once. Could the same invisible entity that explains the perfect symmetry of a neutron also be the hidden mass that binds the stars? Those microscopic quantum tremors from the inflating field did not simply vanish. They were frozen into the very fabric of space-time, etched across the cosmos as a faint blueprint. This is the profound link between the quantum and the cosmic, a connection we can literally see in the sky. The cosmic microwave background, that ancient afterglow from when the universe first became transparent, is not perfectly smooth. It is a tapestry of minute temperature variations, a mottled map of slightly hotter and colder spots. These tiny differences, only one part in 100,000, are the direct imprint of those primordial quantum fluctuations. The slightly denser regions where the inflating field had a tiny extra jiggle became the gravitational seeds for everything to come. After inflation, gravity went to work. Over hundreds of millions of years, these minuscule overdensities acted as anchors. The relentless pull of their extra gravity began to attract the dark matter and hydrogen gas that filled the young universe. Think of a gentle, invisible hillside on an otherwise flat plain. Rainwater naturally flows into the dip, collecting into a puddle. In the cosmos, matter flowed into these gravitational puddles. The small puddles merged into larger ones, growing over eons into vast clouds of gas that eventually collapsed under their own weight to form the first stars and galaxies. The largest of these structures evolved into the immense clusters and superclusters we see today, forming a cosmic web of filaments and voids that stretches across billions of light years. Every galaxy, every star, and every planet exists because of a quantum hiccup that occurred in the first trillionth of a second. The pattern of galaxies in the night sky is a ghostly, magnified echo of the universe's quantum origins. How strange to think that the grandest structures we can observe were all born from the tiniest possible vibrations in an invisible field. Those ghostly quantum fluctuations that built the cosmos are mirrored by another strange sea, one that lies beneath the particles of matter themselves. Our 10th theory takes us back to a revolutionary idea from physicist Paul Dirac. While trying to reconcile quantum mechanics with Einstein's special relativity, his equations produced two solutions. One perfectly described the electron, but the other seemed to describe a particle with negative energy. This was a profound puzzle. To make sense of it, Dirac proposed a breathtaking concept. He suggested that what we perceive as a vacuum is not empty at all, but an infinite, dense ocean of negative energy electrons. This became known as the Dirac sea. In this picture, an ordinary electron is simply a particle that has been lifted out of this sea, leaving behind a tiny hole in the negative energy background. That hole, a missing piece of negative charge and energy, would behave exactly like a particle with positive charge and positive energy. This was the prediction of antimatter. Just a few years later, the positron, the antimatter counterpart of the electron, was discovered in cosmic rays, confirming Dirac's radical vision. Quantum field theory later refined this picture, doing away with the literal infinite sea. In our modern understanding, the electron field fills all of space, and both electrons and positrons are simply excitations of that same single field. A vibration in one direction gives us an electron, a vibration in another gives us a positron. They are two sides of the same coin, born from the same underlying reality. This solved the puzzle elegantly, but it created an even deeper mystery. When particles and antiparticles meet, they annihilate each other in a flash of pure energy. Given that they are created in equal amounts, the Big Bang should have produced precisely equal quantities of matter and antimatter. All the particles should have found their antiparticle partners and mutually destroyed one another, leaving behind a universe containing nothing but light. And yet, here we are in a cosmos made almost entirely of matter. Something must have happened in the earliest moments to break this perfect symmetry, creating a tiny, 1 in a billion excess of matter over antimatter. For every billion antiparticles, there were 1,000,000,001 particles. After the Great Annihilation, that 1 in a billion surplus was all that remained to form every galaxy, star, and planet we see today. The question of what caused this fundamental imbalance remains one of the greatest unsolved problems in physics. Was it a property of a new, undiscovered quantum field, or a subtle crack in the laws of nature themselves that favored existence over oblivion? This profound dependence on quantum fields leads to an even more radical possibility. What if space and time themselves are not the ultimate stage of reality, but merely players in a deeper game? We have been exploring how particles and forces emerge from vibrating fields, but the next logical step is to question the very fabric they exist within. The theory of emergent spacetime proposes that the dimensions of space and the flow of time are not fundamental. They are collective phenomena that arise from the intricate relationships between countless quantum building blocks, much like the temperature of a gas is not a property of any single atom, but emerges from their frantic collective motion. Think of a perfectly still, smooth piece of fabric. From a distance, it appears as a continuous, two-dimensional sheet. But if you bring it close, you see it is actually woven from countless individual threads. The smoothness of the fabric, its ability to bend and stretch, is an emergent property of how those threads are intertwined. In the same way, the smooth, continuous space-time of our everyday experience may be woven from a vast network of quantum information. One of the most compelling clues for this comes from a concept called entanglement entropy. In the quantum world, two particles can become entangled, their fates linked in such a way that measuring one instantly influences the other, no matter the distance. This spooky connection seems to operate outside of space, challenging our very notion of locality. Remarkably, physicists have discovered a deep mathematical relationship between the amount of entanglement between different regions of a quantum system and the geometry of the space they seem to inhabit. The very connectivity of space, the fact that 2 points are close together, might be a direct result of them being highly entangled. If you reduce the entanglement between them, the spatial distance between them grows. It is as if space is being stitched together by these quantum threads. The most concrete realization of this idea is the anti-de Sitter conformal field theory correspondence, often called the holographic principle. This is a profound mathematical duality that suggests a universe with gravity, like our own, can be completely described by a quantum field theory that lives on its boundary in one less dimension. Imagine a sealed spherical room. Everything that happens inside the room, every star, every planet, every event, is encoded like a hologram on the two-dimensional walls of the sphere. The three-dimensional interior, with its gravity and curvature, emerges from the information painted on the two-dimensional surface. In this view, our familiar four-dimensional universe of space and time could be a holographic projection from a vast, complex quantum system existing at the cosmic edge. This is not saying we live inside a literal hologram, but that the laws of physics do not require fundamental dimensions. Space and time are not the starting point, they are the end result. They are the language that emerges when a vast number of quantum components become entangled in just the right way. If this is true, then the Big Bang was not an explosion in a pre-existing void, but the moment when the geometry of space and time first crystallized from a more primitive, non-spatial state. The very stage upon which the cosmic drama unfolds may be the grandest emergent phenomenon of all. What does it mean for our reality if the space we move through and the time we feel passing are merely a compelling illusion born from a deeper, spaceless, timeless quantum reality? This radical idea of emergent space-time finds its ultimate expression in a single, haunting equation. The Wheeler-de Wit equation represents one of the most ambitious attempts to unify general relativity with quantum mechanics to find the quantum description of gravity itself. Its implications, however, are so strange that they threaten to dismantle our most basic experience of the world. The equation successfully combines the principles of quantum theory with Einstein's description of space-time, but in doing so, it produces a result that seems to erase time from the universe. The fundamental wave function of the entire cosmos described by this equation is completely static. It does not evolve, it simply is. This is the infamous problem of time. At the most basic level of reality, according to this framework, there is no past, present, or future. There is no flow, no ticking clock, no before and after. The entire history of the universe is frozen into a single, timeless block. Think of a movie film. We experience reality frame by frame, moment by moment, living through the progression of the story. The Wheeler-de Wit equation suggests that the fundamental reality is not the sequential frames, but the entire reel of film itself, existing all at once. Our vivid, undeniable sensation of time passing, of cause leading to effect, would then be a profound illusion, a shadow cast by a deeper, timeless reality. How can this be? How can our deepest intuition about the world be so completely wrong? The emerging answer from quantum gravity research is that time is not fundamental, but an emergent property, much like temperature. A single atom does not have a temperature. Temperature is a collective phenomenon that only makes sense for a vast ensemble of atoms. In the same way, time may not exist for the fundamental building blocks of the universe. It only emerges when a vast number of these quantum entities interact in a particular way, creating the appearance of a sequence. This challenges the very bedrock of causality. If there is no fundamental time, then the chain of cause and effect, the idea that the past determines the future, loses its absolute meaning. Our lives feel like a story unfolding, but from this grandest perspective, the entire story is already written, with every event eternally present. This does not make our experiences any less real, but it suggests they are part of a vastly larger and more mysterious whole. The flow of time may be the universe's most compelling and necessary illusion, a narrative we are woven into rather than the ultimate stage upon which we act. This timeless, frozen reality described by the Wheeler-de Wit equation finds a strange and powerful echo in a special class of quantum fields. theories where the very concept of size becomes meaningless. These are conformal field theories. In most of physics, scale matters tremendously. The rules governing a planet's orbit are utterly different from those dictating an electron's dance around a nucleus. But in a conformal field theory, the physics remains identical no matter how much you zoom in or zoom out. The system looks exactly the same whether you are observing it from a mile away or with a powerful microscope. This property is called scale invariance. Imagine a coastline viewed from space. You see its general shape, its bays and peninsulas. As you zoom in, you discover smaller bays within those bays, and then even smaller inlets and rocky outcrops. If the coastline were perfectly scale invariant, this pattern would continue forever, with the same intricate, jagged detail repeating at every single level of magnification. There is no fundamental graininess, no smallest unit of the pattern. The entire structure is self-similar. This is not just a mathematical curiosity, it is the key to understanding some of the most dramatic transformations in nature, phase transitions. Think of a block of ice melting into water. At the precise moment of transition, at the critical point, the system becomes scale invariant. You will see tiny, fluctuating domains of ice and water coexisting, with these domains forming at every conceivable scale, from microscopic to nearly the size of the entire block. The physics at that exact critical point does not care about the size of the fluctuations. It is governed by a conformal field theory. This profound connection means that the bizarre, scale-free behavior of a magnet losing its magnetism at a specific temperature is mathematically linked to the quantum fields that describe fundamental particles. The same universal principles govern the frantic dance of molecules in a boiling pot and the quantum jitters of the vacuum. But the true power of conformal field theories is revealed when we push them to their logical extreme in the context of space itself. They form one side of the holographic principle. Remember the sealed room where the entire three-dimensional interior is encoded on its two-dimensional walls. The theory that lives on that boundary wall, the one that perfectly describes the gravity-filled universe within, is a conformal field theory. It is scale invariant because the boundary has no inherent scale of its own. It is just an abstract surface where information is stored. This means that the entire rich, three-dimensional tapestry of our universe, with its planets, stars, and galaxies, could be a holographic projection from a dance of information that has no notion of big or small. The force of gravity, the very curvature of space-time, emerges from the intricate, scale-free correlations within this boundary theory. We are left with a staggering possibility that the cosmos we inhabit is not fundamentally a vast three-dimensional arena, but the emergent consequence of a shimmering, scale-invariant pattern painted on the farthest horizon of reality. Could it be that the universe has no intrinsic size at all, but is simply a pattern that looks the same from any perspective? Even the most enduring cosmic structures can hide a paradox that threatens to unravel physics itself. This conflict centers on black holes, the ultimate endpoints of gravity, and it creates a crisis between our two most successful theories. On one hand, general relativity describes a black hole's interior with serene elegance. An astronaut crossing the event horizon, the point of no return, would theoretically feel nothing unusual at first. It would be a silent, smooth passage into the unknown. But quantum mechanics tells a very different story. It insists that information, the specific identity of every particle that falls in, can never be truly destroyed. The properties of that astronaut, the memory of their life, the precise arrangement of their atoms, this quantum information must be preserved somehow. The paradox is born from this clash. If the astronaut enters the black hole peacefully and the information is trapped inside, what happens when the black hole slowly evaporates, as Stephen Hawking predicted? Hawking radiation, the faint glow emitted by black holes, appears to be completely random, carrying no information about what fell in. When the black hole finally vanishes, all that information would seemingly be erased from the universe, violating a fundamental rule of quantum theory. This is the black hole information paradox, a deep fissure in our understanding of reality. To resolve it, physicists have been forced to consider a truly violent possibility, the firewall. This controversial proposal suggests that the event horizon is not a tranquil gateway. Instead, it is a searing wall of immense energy, a literal barrier of fire created by the frantic quantum corrections trying to preserve information. The moment our astronaut reaches the event horizon, they would be instantly incinerated into a shower of elementary particles. Their information would not be lost because it would never actually cross the horizon. It would be encoded in the radiation blazing from the firewall surface. This solves the information paradox with brutal efficiency, but at a tremendous cost. It shatters the smooth space-time geometry predicted by general relativity. The universe, according to this idea, would be fundamentally unpredictable, with the laws of physics changing dramatically at a boundary that should be unremarkable. The firewall is a desperate solution, highlighting how poorly we understand the marriage of quantum fields and gravity. It forces us to ask whether our concepts of space and information break down completely at the edge of a black hole, revealing a deeper, more chaotic layer of reality. A firewall at the horizon is a violent solution that preserves information by destroying the very fabric of smooth space-time. But what if the solution is not a wall of fire but a hidden bridge? This brings us to a profoundly elegant idea that weaves together the greatest puzzles of the 20th century. It is called the ER=EPR conjecture. The name itself is a fusion of two landmark concepts from Einstein's work. ER refers to the Einstein-Rosen bridge, the formal name for a wormhole, a hypothetical tunnel through space-time connecting two distant points. EPR stands for Einstein-Podolsky-Rosen, the trio who first highlighted the bizarre, spooky action at a distance of quantum entanglement. For decades, these were seen as completely separate ideas, one from general relativity and the other from quantum mechanics. The revolutionary conjecture proposes they are not just related, they are the very same thing. An entangled pair of particles, like two electrons linked across the galaxy, are not communicating through some mysterious, invisible signal. They are connected by a microscopic wormhole, a tiny, non-traversable bridge in the fabric of space-time. Entanglement, the spooky connection, is the quantum manifestation of a physical geometric link. This single idea begins to stitch together the two great pillars of physics, suggesting that the geometry of space-time and the quantum connections between particles are two sides of the same coin. The universe is not just described by quantum fields living in space. Space itself may be woven from a vast, dense web of quantum entanglement. Think of space not as a fundamental void, but as a network of connections. Two points are close together not because of an abstract measurement of distance, but because they are highly entangled. When two particles become entangled, a tiny, Planck-scale wormhole instantly forms between them, stitching their locations together. This provides a breathtakingly simple resolution to the black hole information paradox. What happens to the information of an astronaut falling into a black hole? According to this view, it is not lost at all. The interior of the black hole is not a sealed tomb. It is connected via a vast, complex network of wormholes to the Hawking radiation that has already escaped. Every particle of Hawking radiation is entangled with the black hole's interior. This means the information about the astronaut is not trapped inside the horizon. It is smeared across the entire system, encoded in the correlations between the radiation and the interior. The information was never in one place to be destroyed. It was always distributed across the connected whole. The event horizon is not a fiery wall or a one-way street, but one end of a cosmic tapestry of connections. This vision suggests a reality where the deepest level of physics is not about particles or forces, but about relationships and connectivity. the solidity of space and the strangeness of quantum links might both emerge from a more primitive structure where information and geometry are unified. Could it be that every time we create an entangled pair of particles in a lab, we are unconsciously knitting together the tiniest threads of space-time itself? This beautiful symmetry between entanglement and geometry hints at a deeper order. But what if the universe's underlying mathematics is even more symmetrical than we ever suspected? Supersymmetry is a breathtaking proposal that the cosmos operates with a kind of hidden perfection, a symmetry so profound it connects the two fundamental classes of particles, the fermions that build matter and the bosons that carry forces. In this elegant framework, every known particle has a hidden twin, a superpartner. For every electron, there would be a hypothetical selectron, for every quark, a squark. For the force carrying photons and gluons, there would be photinos and gluinos. These superpartners are not mere copies, they represent a fundamental balance in the cosmic ledger. This pairing creates a new kind of object, a superfield, which elegantly unifies matter and force into a single mathematical entity. The implications of this are staggering. It suggests that at extremely high energies, like those just after the Big Bang, the distinction between a particle of matter and a messenger of force completely blurs. They become different vibrations of the same underlying superfield reality. One of the most compelling reasons physicists are so drawn to this idea is its potential to solve the infamous hierarchy problem, the baffling weakness of gravity. You can think of the fundamental forces as having different strengths. The electromagnetic force is powerful, the strong nuclear force is even more so, but gravity is unbelievably feeble in comparison. A tiny magnet can lift a paperclip, effortlessly overcoming the gravitational pull of the entire Earth. Why is there such a colossal gap between gravity and the other forces? In the Standard Model, this is an ugly, unexplained fine-tuning. The mass of the Higgs boson, and by extension the masses of other particles, is constantly being jostled by its interactions with all the other quantum fields. These quantum corrections should drive the Higgs mass up to a scale quadrillions of times larger than what we measure. To get the tiny mass we observe, the initial bare value of the mass would have to be fine-tuned to an absurdly precise degree to cancel out these enormous corrections, like balancing a pencil on its tip for billions of years. Supersymmetry offers a graceful way out, because every fermion has a bosonic superpartner and vice versa. Their quantum contributions to the Higgs mass come with opposite signs. The huge positive push from one particle is almost perfectly cancelled by the huge negative pull from its superpartner. The fine-tuning vanishes, replaced by a natural, mathematical cancellation born from symmetry. This makes the observed lightness of the Higgs boson not a miracle, but an expected outcome of a more complete theory. So why, after decades of searching, have we not found any of these superpartners? Experiments at the Large Hadron Collider have been meticulously searching for the telltale signs of these particles, but so far, the detectors have remained silent. The simplest versions of supersymmetry predicted these particles should have shown up at the energies we have already probed. Their absence suggests that if supersymmetry is real, it must be a broken symmetry. Much like the Higgs field broke the symmetry of the electroweak force, some mechanism must have given the superpartners immense masses, pushing them far beyond our current ability to create them in a collider. This does not kill the theory, but it does mean the hidden symmetry of our universe, if it exists, lies waiting in a realm of energy we have yet to access. The dream of a perfectly balanced cosmos remains just that for now, a beautiful, untested idea hovering at the very edge of our understanding. The elegance of supersymmetry is not the only path nature might have taken. Another bold class of theories suggests the Higgs boson is not an elementary particle at all, but a composite object, a cosmic mirage built from more fundamental ingredients. These are the Technicolor and composite Higgs models. Their premise turns the Standard Model on its head. we know that protons and neutrons are not truly fundamental. They are made up of quarks bound together by the strong nuclear force. What if the Higgs is the same? In these theories, the Higgs field is not a simple elementary field. It is a condensate, a collective behavior of a whole new set of particles, often called technoquarks, held together by a new, powerful force analogous to the strong force, but operating at a much higher energy scale. This new force is the technicolor force, the entire mechanism of electroweak symmetry breaking, the process that gives particles mass, would then be a direct analog of how protons acquire their mass from the strong force binding quarks. This is a radically different origin story for mass in the universe. The primary appeal of this idea is its natural solution to the hierarchy problem, the puzzling fine-tuning of the Higgs mass. In a composite Higgs model, the Higgs boson is a bound state, and its lightness is not a miracle but a consequence of its size. A proton has a specific mass because it is a specific size, a composite object held together by the strong force. It is not subject to the same wild quantum corrections that plague an elementary Higgs. In this picture, the Higgs boson is heavy and problematic only up to the energy scale of its compositeness, the point where we could probe inside it and see the technoquarks. Beyond that scale, the concept of a fundamental Higgs boson simply dissolves, and the fine-tuning problem vanishes. It is a beautifully economical idea, using a mechanism we already know exists in nature, the binding of quarks into protons, to explain the universe's most mysterious field. While the simplest technicolor models have been largely ruled out by experiment, more sophisticated composite Higgs models remain compelling candidates for physics beyond the standard model. They suggest that the vacuum we inhabit, the very stage for our existence, might be a complex and dynamic substance, more like a superfluid or a crystal than a simple, fundamental field. What other cosmic structures might be hiding their true, composite nature just beyond our current vision? The fundamental forces of nature all speak the language of quantum fields, but gravity remains stubbornly silent. While electromagnetism has the photon and the strong force has the gluon, gravity alone refuses to be quantized in any straightforward way. Yet, the quest for a complete picture of reality demands we try. This leads us to the hypothetical graviton, the proposed quantum of the gravitational field. Just as the electromagnetic field manifests as photons, the gravitational field would manifest its influence through these discrete packets of energy. A graviton would be the messenger particle for gravity, theoretically traveling at the speed of light and conveying the force of attraction between masses. In this picture, the Sun does not simply pull on the Earth through a mysterious, instantaneous grip across empty space. Instead, it constantly emits a stream of virtual gravitons, and the Earth, in turn, absorbs them, creating the continuous dance of their orbit. It is an elegant and compelling idea, one that would finally bring gravity into the quantum family, but the path to unification is littered with profound mathematical challenges. The central conflict arises when we try to merge the smooth, geometric fabric of spacetime described by Einstein's general relativity with the frantic, probabilistic world of quantum field theory. In general relativity, gravity is not a force in the traditional sense. It is the curvature of spacetime itself. Mass tells spacetime how to curve, and curved spacetime tells mass how to move. To quantize gravity is to quantize the very stage upon which the cosmic drama unfolds, and this creates a vicious cycle of infinities. The problem is known as non-renormalizability. In quantum field theory, when you calculate the probability of a particle interaction, you often get an answer that is infinite, which is physically nonsensical. For forces like electromagnetism, a mathematical technique called renormalization can systematically sweep these infinities under the rug, yielding finite, accurate results. But for gravity, this process fails catastrophically. Every time you try to cancel out one infinity, another, more severe one emerges. the calculations spiral out of control because gravity is its own source. The graviton carries energy, and since energy is equivalent to mass, the graviton itself generates a gravitational field. This self-interaction creates a feedback loop of infinite corrections that our current mathematics cannot tame. It is as if you are trying to calculate the exact shape of a reflection in two opposing mirrors, with each reflection containing another, deeper reflection, continuing into an endless, dizzying recursion. This suggests that at the tiniest possible scales, near the Planck length, the smooth geometry of space-time must break down into a quantum foam, a seething, chaotic froth where concepts like before and after, or even here and there, lose all meaning. The search for a theory of quantum gravity is therefore a search for a new language, one that can describe this frothing, dynamic foundation from which both particles and space-time ultimately emerge. How can we hope to understand a universe where the very rules of location are woven from such profound uncertainty? This mysterious inflattened field, the engine of cosmic inflation, was not a permanent feature of the cosmos. Its reign of exponential expansion had to end, and the way it ended created everything. The process is often described as a slow roll. Picture the inflattened field as a marble resting high up on a vast, gentle hill, a landscape representing its potential energy. The height of the hill is the immense energy that drove the violent expansion of space. As the universe expanded, the field slowly rolled down this slope. For a fleeting instant, it was caught in a state of false vacuum, like a marble momentarily stuck in a small dip on the hillside, still possessing tremendous energy. But as it continued its inevitable descent, it finally reached the steep part of the slope, picking up speed and oscillating wildly at the bottom of the valley. This frantic oscillation was the key to everything. The immense potential energy the field had been storing was now rapidly converted into a hot, dense soup of familiar particles, a process known as reheating. It was the true Big Bang moment, the fiery genesis of the matter-filled universe we know. In a spectacular flash, the energy of the inflattened field gave birth to quarks, electrons, photons, everything. All the raw material for every star, planet, and living thing was created in that cosmic transformation. The inflattened field itself decayed away, its job complete, leaving behind the hot, expanding plasma of the early universe. But it left a permanent calling card. The quantum jitters that rippled through the inflattened field during its slow roll were stretched to cosmic proportions by inflation and frozen into the fabric of the newborn universe. These minute variations in density became the seeds for all future structure, and they left a faint but unmistakable imprint on the oldest light we can see. When we map the cosmic microwave background, we are essentially reading a baby picture of the universe, a snapshot of those density variations imprinted by the inflattened field's quantum tremors. The specific patterns of hot and cold spots in that ancient light are a direct record of the inflattened's properties, its mass, and the precise shape of its energy hill. We are, in a very real sense, seeing the ghostly fingerprint of the field that birthed our entire cosmic reality. What does it mean that the largest structures in the universe carry the memory of the smallest possible quantum vibrations? Dark energy is a ghost in the equations, a placeholder for our ignorance. But what if the force accelerating the cosmos is not a constant energy of the vacuum, but something far more dynamic and cunning? This leads us to the theory of the chameleon field, a hypothetical entity that actively hides from us. Its entire nature is defined by evasion. Unlike the Higgs field, which is constant everywhere, a chameleon field changes its mass and interaction strength based on its surroundings. In the dense, crowded environment of a laboratory or within our solar system, the field becomes extremely heavy and short-ranged, effectively shutting itself off and becoming nearly impossible to detect. It squeezes itself into a tiny corner of reality, but in the vast, empty deserts of intergalactic space where matter is sparse, the chameleon field becomes light and long-ranged. Its pressure then emerges, pushing space apart and mimicking the effects of dark energy. It is a cosmic shapeshifter, a fifth force of nature that only reveals its true power where no one is looking. This is a brilliant solution to a major problem. For decades, proposals for modified gravity, alternatives to Einstein's general relativity, have been plagued by a simple question. If there is a fifth force, why don't we see its effects in our precise solar system tests? The chameleon field answers with a simple, elegant mechanism, a screening effect that suppresses the force in high-density regions. It hides in plain sight. Testing for such a shy entity requires extraordinary ingenuity. You cannot build a box to trap it because inside the box it would simply vanish. Instead, we must go to the emptiest places we can find or use the most delicate probes imaginable. Upcoming space telescopes and missions are designed to do exactly that. They will look for subtle deviations in the orbits of distant stars around the galactic center, a region where the chameleon's influence might subtly alter their paths. Other experiments will use ultra-cold atoms in the near-perfect vacuum of space, sensitive enough to feel the faintest whisper of a force that refuses to be seen on Earth. We are essentially setting a trap for a ghost by studying the emptiness between galaxies. The quest is to catch the universe in an unguarded moment, to witness a fundamental force as it forgets to hide. What other cosmic secrets are concealed not by distance but by their own clever design? The chameleon field hides its power, but another phantom field could unleash its full force with cosmic violence. This is the phantom field hypothesis, a version of dark energy so extreme it predicts the universe will end not with a whimper but with a scream. While the cosmological constant represents a gentle, steady pressure, the phantom field is a form of quintessence with a terrifying property. Its negative pressure grows stronger over time. Think of dark energy as a kind of cosmic accelerator. The standard model puts its foot on the gas pedal and keeps it there, leading to a steady, accelerating expansion. The phantom field, however, is an accelerator that gets pressed down harder and harder forever. The result is an exponential runaway effect. The expansion rate does not just increase, it skyrockets towards infinity. This leads to the most dramatic in-game scenario imaginable, the Big Rip. The timeline of this cosmic dissolution is calculated from a single parameter, the equation of state. If this value drops below a specific threshold, the phantom field takes over destiny. First, the phantom energy would overcome the gravitational glue holding galaxy clusters together. Billions of years from now, these vast islands of stars would be flung apart into the growing void. Next, as the expansion accelerates to unimaginable speeds, it would tear apart individual galaxies. The Milky Way would be shredded, its stars scattered into the endless, empty darkness. The horror would then come closer to home. With the expansion rate now incomprehensibly vast, the phantom energy would attack our own solar system. The sun's gravity would be overcome, and the planets would be ripped from their orbits, flying off into the nothingness. In the final moments, the forces that hold matter itself together would be defeated. The same repulsive energy would overwhelm the electromagnetic force binding atoms, and then the strong nuclear force holding atomic nuclei together. In the last fraction of a second, every molecule, every atom, every proton and neutron in the universe would be violently torn asunder. The cosmos would be reduced to a thin, cold mist of disconnected elementary particles, forever flying apart, unable to ever interact again. Based on current observational data, this apocalyptic finale is not the most likely outcome, but it remains a possibility lurking within the margin of error. If the phantom field is real, calculations suggest this end could come in as little as 22 billion years. The universe would die not in fire or ice, but in a storm of absolute disintegration. What would it mean for reality if the very vacuum of space holds a latent fury powerful enough to unravel existence itself? A universe tearing itself apart is one possible ending, but the laws of physics might permit an even stranger form of travel. Tachyonic fields are theoretical constructs where the most fundamental particles are born already moving faster than light. The name tachyon comes from the Greek word for swift, and it describes a state of existence that is completely inverted from our own. For us, objects with mass can never reach the speed of light. It is a cosmic speed limit, but a tachyon, according to the mathematics, could never slow down to the speed of light. It is forever trapped on the other side of that barrier. This is not about acceleration, but about a fundamental property of its being. A tachyon would have an imaginary mass, a mathematical term meaning its mass, when squared, gives a negative number. This bizarre property is not a description of a real particle we might find, but rather a signpost in our equations pointing to a profound instability. When a physicist sees a tachyon appear in a calculation, it is not a signal to build a faster-than-light starship. It is a red flag indicating that the current configuration of the universe or of a particular field is unstable and poised to collapse into a more stable state. This is precisely the role they play in spontaneous symmetry breaking. Recall the image of the Mexican sombrero with the unstable peak and the stable valley. A field sitting at that high, symmetric point is in a tachyonic state. It is teetering on the brink, and any tiny fluctuation will send it rolling down into the valley, breaking the symmetry and settling into the stable, non-zero value we observe today. The Higgs field, before it gave mass to the universe, was in such a tachyonic condition. It was a field poised to fall, and its fall created the world as we know it. So why don't we see actual tachyons zipping through the cosmos? Because they are not stable particles. They are the ghosts of a transition, the momentary shiver of a field as it settles into its true, stable vacuum. They represent a state that the universe has already moved through and left behind. The idea of faster-than-light travel, while captivating, is likely a mirage created by misreading the mathematics of instability. The true legacy of the tachyon is not an engine for starships, but a fundamental message about the nature of reality, that our stable world was born from a moment of profound cosmic imbalance. The universe seems to have a deep-seated preference for symmetry, yet it is the subtle cracks in that perfection that allow us to exist at all. One of the most beautiful examples of this dance between symmetry and its breaking lies in a hypothetical field proposed not to create mass but to preserve a delicate cosmic balance. This is the Peck-Quinn field, an elegant solution to the strong CP problem. Remember the puzzlingly perfect symmetry of the neutron, which refuses to have a slight electric imbalance despite the laws of the strong nuclear force suggesting it should. Roberto Peck and Helen Quinn asked a profound question: what if this symmetry is not a fundamental law, but the result of a new dynamic field? They proposed the existence of a cosmic field that adjusts itself throughout the universe, naturally cancelling out the unwanted CP violation in the strong force. It is as if the universe has a built-in thermostat, one that constantly fine-tunes itself to maintain the perfect, round neutrality of every neutron. This mechanism is not forced, it emerges naturally from the field's desire to settle into its lowest energy state. The moment this field was conceived, it made a stunning prediction. Just as a vibration in the Higgs field gives us the Higgs boson, a vibration in the Peck-Quinn field would manifest as a new, ultra-light particle, the action. This particle would be the quantum whisper of this cosmic correction, a ghostly signature of the universe's own effort to stay balanced. The action would be staggeringly light, potentially 1 trillion times lighter than an electron, and interact with ordinary matter only with the faintest of touches. This makes it incredibly difficult to detect, but also a perfect candidate for the cold dark matter that holds galaxies together. For decades, physicists have been on a grand hunt, building exquisitely sensitive experiments to listen for the action's faint signal. These detectors are like cosmic radios, scanning the dark matter halo of our galaxy for a specific, incredibly weak note. They use powerful magnetic fields to try and coax a passing action into transforming into a single, detectable microwave photon. The challenge is immense, akin to trying to hear the flutter of a single snowflake landing in the middle of a roaring concert. Despite this, the elegance of the Pexi-Quinn solution is so compelling that the search continues to intensify. New experiments are pushing the boundaries of quantum sensing, exploring different mass ranges and coupling strengths. The fact that we have not found it yet does not kill the theory. It simply means the action is even more elusive than we first imagined. This decades-long search for a particle born from a need for cosmic symmetry highlights a deep truth about our universe. Its most fundamental secrets are not always shouted, but often whispered in the quietest corners of physics. These cosmic symmetries, once broken, could have left behind not just new particles, but monumental scars in the fabric of space. When a quantum field cools and settles into its new state, it does not always make the same choice everywhere at once. Picture a vast, hot vat of molten metal. As it cools, different regions begin to crystallize randomly. Where these randomly oriented crystal domains eventually meet, the atoms cannot line up perfectly, creating a permanent defect, a dislocation in the metal's structure. The early universe underwent a similar process on a cosmic scale. As the hot, symmetric plasma of the Big Bang cooled, different regions of space underwent phase transitions independently, and the resulting patches of the new vacuum did not always match up. The boundaries between these mismatched patches became frozen into the cosmos as topological defects, exotic structures that could be the most ancient relics in existence. One of the most dramatic of these fossils is the cosmic string. These are not strings in the everyday sense, but incredibly thin, unimaginably dense filaments of energy, thinner than a proton, but with the mass of a mountain range packed into every centimeter. A single cosmic string could be as long as a galaxy, a flaw in spacetime so severe that it warps gravity around it. If one were to pass through the solar system, it would not pull planets inward, but would instead create a unique gravitational lensing effect, potentially causing double images of distant stars without any visible cause. Another possible defect is the domain wall, a two-dimensional sheet of concentrated energy separating vast regions of space where the quantum field settled into different values. A domain wall would be a terrifying structure, a membrane with a gravitational field so intense that anything on one side would be pulled toward it with immense force. Thankfully, most theories suggest such walls would be unstable or would have dominated the universe long ago, and their absence is a key clue that helps physicists rule out certain models of cosmic evolution. Then there is the magnetic monopole, a hypothetical particle that is a single, isolated magnetic pole. Every magnet we know has both a north and a south pole, but a monopole would be a pure north or a pure south, a fundamental point-like defect predicted by many grand unified theories. These defects are not just theoretical curiosities. Their presence or absence tells a profound story about how the universe cooled. The fact that we do not see a universe filled with domain walls or magnetic monopoles is a crucial piece of evidence, telling us that the early universe's phase transitions must have happened in a specific, smooth way. The hunt for these cosmic fossils is now a major astronomical pursuit. Astronomers search for the telltale double images of galaxies caused by the gravitational lensing of a cosmic string. They analyze the cosmic microwave background for the distinctive temperature patterns a passing string would create. Finding one would be like discovering the fossilized bone of a primordial giant, a direct snapshot of the universe in its first furious moments of formation. These defects are the cosmic equivalent of cracks in a potter's glaze, the inevitable imperfections that reveal the history of its creation. What other monumental structures, born from a single misaligned choice, might be hiding in the vast darkness between the stars? Our most basic assumption is that a vacuum is simply empty, yet the very act of acceleration can conjure particles from this apparent void. This is the Unruh effect, a prediction of quantum field theory so strange it forces us to question what a particle even is. An observer drifting through space, completely weightless and moving at a constant velocity, looks out at the universe and sees a perfect vacuum. Their detectors register nothing, just the serene emptiness of space. But now, imagine another observer who fires their rockets, accelerating relentlessly through that same patch of cosmos. This astronaut, pinned to their seat by the force of acceleration, would point their identical detector at the very same vacuum and see something entirely different. Their instruments would click and whir, registering a warm bath of particles, a gentle heat emanating from the nothingness itself. Both observers are correct in their own frame of reference. The vacuum itself is not an absolute state. It is a relative experience defined entirely by your motion. The key to this bizarre phenomenon lies in the nature of the quantum fields that fill all of space. Even in what we call empty space, these fields are never truly still. They are subject to quantum fluctuations, a seething foam of virtual particles that wink in and out of existence. For the inertial observer gliding smoothly, these fluctuations average out to zero, appearing as nothing. But for the accelerating observer, their motion through this frothing quantum soup creates a kind of friction. The relentless acceleration effectively drags along a region of the field, stirring up the virtual particles and giving them enough energy to become real, detectable particles. The spectrum of these created particles is exactly that of thermal radiation, a perfect heat bath. The temperature of this phantom glow is directly proportional to the acceleration. The harder you push on the rockets, the hotter the ghostly fire around you becomes. For accelerations we can achieve, this temperature is utterly minuscule, far too cold to ever detect. But for a theoretical observer hovering just outside the event horizon of a black hole, where gravity produces an immense acceleration, the effect becomes significant and is deeply connected to the Hawking radiation that black holes emit. This reveals a profound truth: particles are not fundamental entities in their own right. They are excitations or vibrations that we define by how we interact with the underlying quantum fields. Your state of motion literally determines what you perceive as real. This shatters the classical idea of a universal vacuum and replaces it with a fluid, observer-dependent reality where existence itself is a matter of perspective. What does it mean for our understanding of the universe if even the particles that compose it are not absolute, but emerge from our own journey through the cosmic fields? The ghostly glow of Unruh radiation reveals that particles are not absolute, but a direct consequence of our motion through the quantum fields. But what if you could reach out and physically feel the pressure of this seething vacuum? This is not science fiction. It is a measurable force known as the Casimir effect, and it provides our most direct evidence that empty space is alive with activity. The phenomenon is named after the Dutch physicist Hendrik Casimir, who predicted it in the 1940s. He envisioned two perfectly smooth, uncharged metal plates placed incredibly close together in a perfect vacuum, parallel to each other. According to classical physics, with no electric or gravitational forces at play, nothing should happen, but the quantum world tells a different story. The space between the plates restricts the kinds of quantum fluctuations that can exist there. Only those fluctuations whose wavelengths fit perfectly between the plates, like musical notes on a string of a specific length, are allowed. Outside the plates, however, the quantum foam can buzz with fluctuations of all possible wavelengths. This creates a pressure imbalance. The riot of activity outside the plates pushes them together with more force than the limited set of fluctuations pushing from within. The result is a tiny but measurable attractive force pulling the plates towards each other. It is as if you were in a crowded swimming pool and you held two large, flat boards just inches apart. The people representing the quantum fluctuations can push on the boards from the outside, but very few can fit in the narrow space between them to push back. The boards are forced together by the crowd. This is not just a theoretical curiosity. The Casimir effect has been confirmed in multiple, precise laboratory experiments. Scientists use plates, often replaced by tiny gold-coated spheres and flat surfaces, and bring them to within nanometers of each other. At these microscopic distances, the force becomes significant, and the attraction has been measured to an astonishing degree of accuracy, matching the predictions of quantum field theory. This is a breathtaking validation. We are not just inferring the existence of quantum fluctuations, we are measuring their physical push. The implications ripple out from fundamental physics into the realm of practical technology. In the burgeoning field of nanotechnology, where engineers build machines on the scale of molecules, the Casimir effect is no longer a minor curiosity. It is a major design constraint. The tiny moving parts in a micro-electromechanical system can suddenly stick together due to this vacuum force, a phenomenon known as stiction. But with understanding comes the potential for control. Researchers are exploring ways to manipulate the effect, perhaps by using materials with different electrical properties to create a repulsive Casimir force, which could lead to frictionless nanoscale bearings and revolutionary new devices. On a more profound level, the Casimir effect gives us a tangible handle on the vacuum energy. By measuring the force between objects of different shapes, we are essentially taking the temperature of the vacuum itself, probing the spectrum of its endless, frantic activity. This direct link between the abstract quantum foam and a measurable mechanical force is a stunning reminder that the nothingness around us is perhaps the most something thing we know. If the vacuum can push on plates, what other invisible pressures are shaping the cosmos in ways we have yet to perceive? The solidity of space itself may be the universe's most magnificent illusion. This brings us to a theory so profound it redefines the nature of dimensions and information. The holographic principle suggests that our seemingly three-dimensional universe, with all its stars, planets, and people, might be nothing more than a projection, a cosmic hologram encoded on a distant two-dimensional surface. The mathematics points to a reality where the true, fundamental description of the cosmos requires one less dimension than we experience. It is as if the entire rich, three-dimensional world of a sealed room, with every object and event inside it, is actually a perfect, shimmering image painted on the walls of the room itself. The three-dimensional interior, in all its complexity, emerges from the information stored on the two-dimensional boundary. The most concrete realization of this staggering idea is a specific mathematical duality known as the anti-de Sitter conformal field theory correspondence, or AD-SCFT. This is not a vague analogy, but a precise one-to-one dictionary that translates between two seemingly different worlds. On one side of this duality is a universe with gravity, a warped space like the interior of our hypothetical room. On the other side is a quantum field theory that lives on the boundary of that space, a theory that has no gravity at all, but is scale invariant, meaning it looks the same at every level of magnification. The miraculous claim is that these two descriptions are completely equivalent. Every single phenomenon involving gravity and curved space in the interior can be perfectly translated into a complicated interaction of quantum fields on the boundary, and vice versa. A star collapsing into a black hole in the three-dimensional bulk is exactly the same as a specific thermal state heating up on the two-dimensional boundary. This provides a breathtakingly elegant path toward a theory of quantum gravity. The very force that has resisted quantization for a century, gravity, may not need to be quantized on its own terms at all. Instead, it simply emerges, a natural and inevitable consequence of the way a vast number of quantum degrees of freedom become entangled on a lower dimensional surface. The force we feel as gravity and the space we move through could be the collective behavior of a cosmic quantum system that exists at the very edge of everything we know. If this is true, then the Big Bang was not an explosion in a void, but the moment this cosmic hologram first flickered into being, crystallizing a world of depth from a flat, information-rich surface. Are we living inside the most complex projection imaginable, where the third dimension is a compelling shadow cast by a deeper, flatter reality? Even the grand inflation that birthed our cosmos may not have been a one-time event. The mechanism that smoothed our universe appears to be self-replicating, leading to a reality without end or beginning. This is eternal inflation, a process where the fabric of space-time is caught in an endless cycle of runaway expansion. Picture the inflationary field not as a single rolling marble, but as a boiling pot of water that never stops bubbling. Each bubble is a region where the inflattened field has decayed, settling into a stable, low-energy state. Within that bubble, inflation stops and a hot, matter-filled universe like our own is born. But the space between these bubbles, the boiling water itself, continues to inflate at an exponential rate. This rapid expansion constantly creates more room for new bubbles to form. The process is eternal, with new universes endlessly nucleating within an ever-growing, inflating background. Each of these bubbles is a separate universe forever disconnected from our own. They are not floating in a pre-existing void, but are pinpricks of stable vacuum in an eternally stretching sea of high-energy inflation. The profound implication is that the multiverse is not just a collection of universes, it is a dynamic, ever-breeding cosmic landscape. Within this infinite foam, the conditions can vary dramatically. The key lies in how the inflattened field decays within each bubble. This decay process, the way the field settles into its stable state, determines the local laws of physics for that universe. It sets the strengths of the fundamental forces, the masses of elementary particles, and even the number of spatial dimensions. In one bubble, the weak nuclear force might be slightly stronger, preventing hydrogen from fusing into helium and leaving a universe forever dark. In another, the cosmological constant could be immense, tearing that universe apart in a flash. Our universe, with its specific, finely tuned constants that allow for galaxies, stars, and life, is simply one of countless outcomes. We do not live in a special universe, we live in one of the rare, habitable bubbles where the cosmic lottery produced a winning ticket. This cosmic landscape forces a radical shift in perspective. The fundamental constants we have worked for centuries to measure are not universal laws etched into the bedrock of reality. They are more like local weather patterns, the unique climate of our particular cosmic bubble. The deep questions of why the universe is the way it is find a new, unsettling answer, because if every possible set of laws exists somewhere, then our existence is not a mystery to be solved but a selection effect. We could not observe a universe that did not allow for observers. This idea, the anthropic principle, moves from a philosophical curiosity to a potential scientific explanation within the context of an infinite multiverse. The cosmos becomes less a perfectly engineered machine and more a vast, chaotic garden where every possible form of reality blossoms into being. What does it mean for our search for meaning if our entire reality is just one accidental paradise in an infinite and unobservable froth? The smooth stage of space-time we take for granted is not always so cooperative. When the fabric of the cosmos warps under the weight of massive objects, our elegant quantum field theory must learn to adapt. Extending its rules to these curved backgrounds reveals a universe even stranger than we anticipated. The central challenge is that the very definition of a particle becomes ambiguous. In the flat, tranquil spacetime of special relativity, everyone agrees on what constitutes a vacuum and a particle. But in the violently curved geometry around a black hole, that universal agreement shatters. What one observer sees as empty space, another might see as a raging storm of particles. This is the key to understanding one of the most profound discoveries in theoretical physics, Hawking radiation. It is the gravitational cousin of the Unruh effect. Just as an accelerating observer detects a warm glow from the vacuum, an observer held static just outside a black hole's event horizon fighting against the immense gravitational pull to stay in place, would also see a thermal bath of particles. Stephen Hawking realized that from the perspective of an observer far away from the black hole, this effect manifests as the black hole itself radiating heat. The intense gravity near the event horizon acts as a factory for particle pairs. Normally, a virtual particle and its antiparticle partner pop out of the vacuum and almost instantly annihilate each other. But if this happens right at the precipice of the event horizon, one member of the pair can fall inward while the other escapes into space, forever separated from its partner. The escaped particle becomes real, carrying away a tiny amount of the black hole's energy. To the distant astronomer, it appears the black hole is glowing, slowly evaporating over trillions of years. This means black holes are not truly black, nor are they eternal. They have a temperature and a finite life, yet this beautiful mechanism conceals a deep puzzle known as the trans-Planckian problem. The particles that make up Hawking radiation, when we trace their origins back to the very moment they were born, seem to come from waves of impossibly high frequency. As a quantum wave falls toward the event horizon, its frequency is shifted to higher and higher values by the extreme gravity, like a siren's pitch rising to an infinite scream. Just before it contributes to the Hawking radiation we see, its wavelength becomes shorter than the Planck length, the scale at which our current understanding of spacetime completely breaks down. This suggests that Hawking's original calculation relies on physics in a realm where we know our theories are incomplete. The existence of Hawking radiation seems to depend on phenomena occurring in a domain where quantum gravity must reign, a territory we have not yet mapped. So, while we are confident black holes evaporate, the full story of how they die and what truly happens at the edge of nothingness remains hidden within the quantum foam of spacetime itself. How can the final fate of a cosmic giant depend on a reality we cannot yet describe? The mathematics of quantum fields might be pointing toward a reality that is not just strange but programmed. This final theory ventures into one of the most provocative ideas of all, the simulation hypothesis. It asks a startling question: could the universe we perceive be an immensely complex computational construct, and could quantum fields be the very pixels of this cosmic display? The argument begins with a simple observation about the nature of information. Our most advanced theories of quantum gravity, like loop quantum gravity, suggest that space itself is not a smooth continuum. Instead, it appears to be granular, composed of tiny, discrete units of volume. This is a universe with a finite, if astronomically large, information density. There is a fundamental limit to how much data can be stored in any given region of space, a concept known as the Bekenstein bound. This pixelation of reality at the Planck scale mirrors the way a digital screen is composed of individual pixels. Each pixel can only display a finite amount of information, and the resolution is so high that the underlying grid is invisible to the naked eye. In the same way, the smooth, continuous fields we talk about, the electromagnetic field, the electron field, the Higgs field, might not be fundamental. They could be a high-level, emergent approximation of a reality that is, at its core, a vast array of discrete information bits processing according to a set of underlying rules. The quantum field would then be the rendered image, the smooth graphical output generated by a cosmic computer's processor. The probabilistic, quantized nature of quantum mechanics fits eerily well within this framework. In a simulation, processing power is a finite resource. It would be computationally wasteful to calculate the exact path of every single electron in the universe. Instead, a simulation might only render the definite properties of a particle at the moment it is observed, much like a video game only renders the parts of the world the player is currently looking at. The wave function collapse could be the universe's way of optimizing its rendering load. The constant buzz of quantum fluctuations could be seen as the background thermal noise of the processor, the inevitable rounding errors in a calculation of finite precision. Even the speed of light, the ultimate speed limit, could be the clock rate of the cosmic central processing unit, the maximum speed at which information can be transmitted between one point in the simulation and another. This is not to say we are living in a simple video game created by some advanced teenager. The level of complexity required to simulate every quantum field interaction in a single atom, let alone a whole universe, is beyond any comprehension. The programmers, if they exist, would be entities whose technology is indistinguishable from the laws of nature themselves. The simulation hypothesis is ultimately untestable and unfalsifiable with our current knowledge, placing it firmly in the realm of metaphysics. Yet it serves as a powerful mirror for our own understanding. It forces us to confront the fact that our most fundamental description of reality is becoming increasingly mathematical and informational. We are discovering that the universe runs on code, whether that code is written in the language of quantum field theory or in something deeper. The question then shifts from "are we in a simulation" to "does the distinction even matter?" If the quantum fields are so perfectly real that they give rise to our consciousness, our love, and our quest for understanding, then the nature of their substrate may be the ultimate unanswerable question. Is the cosmos a magnificent, self-calculating equation, or could it be the ultimate expression of a different kind of mind? From the ghostly whispers of the Dirac sea to the violent potential of a phantom field, this journey reveals a cosmos far grander and more mysterious than we ever dreamed. We have ventured from the infinitesimal vibrations that became galaxies to the chilling possibility that our reality is a holographic projection. We have seen how empty space is not empty, but a seething ocean of energy, and how the very laws of physics might be local accidents in an infinite multiverse. The solid ground of reality dissolves beneath our feet, replaced by a dynamic tapestry of quantum fields, a cosmic mattress where particles are mere notes in an eternal symphony. This new understanding is a profound revolution, connecting the fate of a falling astronaut to the quantum entanglement that may stitch space itself together. It challenges our most basic assumptions about time, matter, and existence, suggesting that what we perceive is only a shimmering surface on a depthless ocean of strangeness. The universe is not a collection of things, but a complex web of relationships and interactions, a dance of fields whose melodies compose everything from the atoms in your hand to the farthest reaches of the cosmos. Which of these 30 theories reshaped your view of reality the most? Was it the cosmic balancing act of the cosmological constant, the eerie silence of the black hole firewall, or the thought that space and time are themselves an emergent illusion? Let us know in the comments which idea captivated you, and subscribe to continue unraveling the deepest mysteries of the cosmos together.